Good day to everybody. Welcome to the class on computer architecture and operating systems. We have learned to write programs. A program is a piece of software which needs hardware platform to execute it. This hardware platform consists of many systems and subsystems like central processing unit, arithmetic and logic unit, control unit, memory unit, I/O devices, bus structure, etc., and many components like program counter, stack pointer, flags, registers, etc. In the computer architecture classes, we'll know about what these systems, subsystems, and components are made of, what are their functions, how they are interconnected, and how do they communicate amongst each other to do a job, that is to run a program. Now, the bare machine, though extremely powerful, is very difficult to use. Operating systems have been developed so as to give a very friendly environment to the program that is running. Modules of the operating systems are always existing in the memory so as to provide the user a hospitable interface and a friendly runtime environment. The other responsibility of the operating system is to manage the hardware and software resources towards their optimal use. Now, first, to know what the functions of the different systems and subsystems are, let us take a high-level language program and see how a computer executes it. I have taken a high-level language program, say only consists of 3 statements. It's a typical high-level language program. I am not talking about a particular high-level language one. For example, in the case of a C language, this statement instead of read xy possibly will be scanf xy. Similarly, in the case of a Fortran, this will be read and so on. Okay. Now, for this is a kind of a, I should say an example of a high-level language program. Let us see what this high-level language program is doing. Here it is reading 2 variables, read x and y, and adding these 2 variables, x plus y, and assigning it to z, and printing this variable, that means the z. Okay. Now, by this time you know that this high-level language program cannot be directly executed by means of the hardware. So, a translator translates, and I take that the translator first translates it into an assembly language code. Okay. Now, it's a typical assembly language code I have seen. It's not a particular assembly language code of a particular machine, right? Say this read xy will be translated into a statement in here will mean that it will be inputting from some standard input device, okay, and then store accumulator x, that means whatever has been inputted will be stored into the memory location x. Now, I have assumed here that I am talking of a computer in which it's accumulator based. That means it has an accumulator where if I input something, it comes directly into that accumulator. And if I want to store something from the accumulator, I can use an instruction like store accumulator x. Okay. I have also assumed that whenever I'm inputting, a word consisting of 2 bytes is inputted. That means the variable x consists of 2 bytes. Okay. But that's not always the picture, but some simplifying assumptions I have made so far as this assembly language program is concerned. Now, this, as you know, this assembly language programs is essentially a symbolic mnemonic form of a machine language program. We'll come to the machine language. Okay, that means this assembly language also is not the program which is directly executed by the machine. It has to be converted into machine language from the assembly language by means of what we call an assembler. Now, let's see first come to this assembly language program. Say, coming once more, that it is inputting, I'm assuming that there's only one input device. It is inputting a value of 2 bytes into the accumulator, then it's storing that accumulator value into the location X. That is, read X is over, then it is read Y in once more. That means from the standard input device, another 2 byte is read, and then it is storing that accumulator into Y location. Then here I am computing Z is equal to X plus Y. What I am doing is there, from the memory location X, I am loading into that accumulator, the 2 byte, load accumulator X. Okay. Then I am saying that to that accumulator, add the content of memory location Y. Okay. Add memory Y. Then after this addition is over, the result will be in that accumulator itself, and here I'll have to send the result into Z. So I am saying here the stored accumulator Z. Now what is the content of that accumulator? It will be stored into the location Z. Here you see that load accumulator, add memory, store accumulator, all of them are essentially mnemonic instructions. Okay, it has its corresponding machine language version. We come to it, and X, Y, Z are symbolic variables. Okay, names of the variables given symbolically. That means it's memory location which is represented by symbol X, Y, and Z. Now, after Z has been computed, we say that print Z. That means whatever is in that accumulator, you see the result is still in that accumulator. Though I have stored accumulator into Z location, the result X plus Y is still in that accumulator. So if I say out, that means whatever is in that accumulator, it is outputted to a standard output device. Then essentially, as if that is a printer, then print Z instruction is executed. Now this assembly language code is not also, as I said, is the code that will be executed by the machine. The machine will execute what we call that machine language code. Okay. Therefore, from the assembly language code, as I said, it will be translated once more by means of an assembler into this machine language code. Now, I have chosen here the machine language code, okay, as this. For example, in is an assembly language code whose corresponding machine language code in hexadecimal is 01. Now, all the figures that pink that I have shown here are all in hexadecimal, okay, which means, for example, 0 and 1, 0 is a hexadecimal character, 1 is an hexadecimal character, and by this time I hope that you know that what is an hexadecimal, but just to recapitulate that, say a 4-bit binary numbers we have taken, there can be 16 possible combinations of these 4-bit, okay, 0, 0, 0, 0, then 0, 0, 0, 1, 0, 0, 1, 0. That way there can be 16 possible combinations of these binary bits. As you know that the decimal equivalent of this binary I have given in green, okay, this is 0, this is 1, this is 2, and so on. This is up to 15. Now, in the case of an hexadecimal, you see, in the case of a decimal is this, the problem is this, if I want to represent these 4 binary bits, after 9, I'll have to use 2 characters, which I do not want to permit and which is inconvenient. So I represent these binary 16 combinations by means of an hexadecimal character. Up to 9, we keep the characters same, and 10 is represented by A, 11 by B, 12 by C, 13 by D, 14 by E, and 15 by F. Okay, the hexadecimal characters are from 0 to F. For example, now, if we have, say, an hexadecimal figure 04, right, say 04, essentially what I mean is this 0 is 0, 0, 0, 0, and this 4 is 0, 1, 0, 0. You see, this is 4. Therefore, when I say that 0, 4 in hexadecimal, this turns out to be 0, 0, 0, 0, 0, 1, 0, 0 in binary and 8-bit binary. Each hexadecimal is mapped into a 4-bit binary. That way is what I have represented the machine language code. Okay, actually it will be ultimately in binary when it will be loaded into the memories of the computer. Now I have assumed that IN has a machine language operation code 01, right? This is an instruction or opcode or operation code which tells the machine that something has to be inputted from that input device, right? Similarly, the stored accumulator X, the stored accumulator instruction is 04, okay, and that X is a symbolic address of a memory location. I have assumed that the memory location address of that memory location is 0F00, which means that from here that I have assumed that an instruction opcode is of 8-bit or 1 byte. The address of a variable can be of 16-bit, 4 hexadecimal character. Put side by side will make 16-bit binary number, which will be the address of this symbolic address X. Okay, therefore, 040F00 means that it is an instruction to store the content of accumulator into the location 0F00. Okay. Similarly, in 01, that means I'm inputting another value, and then I'm storing this accumulator into the location, symbolic location y, which I have assigned the location 0F02. Okay. Now, here it is load accumulator of operation code or instruction code. I have assumed to be 03. Then from 0F00 location, I am loading the accumulator once more, adding the content of y, that means content of 0F02, and then storing the result into the location 0F04, and then saying that print the result by the instruction out, which has an opcode of 02. So this way, I wanted to just emphasize one thing, that every assembly language, okay, has more or less a counterpart in machine language, and that machine language consists of two parts generally. One is that operation code part, and another is that operand part. In that assembly language, I have represented it by means of a symbol X. In the machine language, that operand address has been shown by means of an hexadecimal string of characters, right? Sometimes that address may not be there. For example, IN doesn't need an address because IN's address is implicitly the accumulator itself, and therefore need not be given explicitly. Now, another thing is apparent from here, that I am talking about, as I said, that is an accumulator based machine. That means the arithmetic operations results are kept in that accumulator. For example, when I have added, the result is in that accumulator. And the second point is that it is a single address machine. That means every instruction has at most one address. Okay, say STA has an one address, then load accumulator has a single address, and so on. That is why this is, I'm talking about as if a single address accumulator based machine. Okay. Now, let us further examine it and try to see that how the computer will execute it. Okay. Now, here you see that this machine language version as have been generated as an output of this assembler has been loaded into the memory location. Here I have shown, you see, that as if it is the memory. Each memory location consists of 1 byte. The black figures gives me the address of that memory location, and the pink gives me the content of that memory location. Okay. Here I have assumed that my program has been loaded from the location, hexadecimal location 0300. Okay. This first instruction is in, and that has been loaded in the location 0300. The machine code is 01, which has been loaded over here. Okay. The second instruction, you see that store accumulator X 040F00. 04 is opcode. This is the address part. Okay. That second instruction has been loaded starting from the location 0301. So 04000F. These 3 bytes taken together is a store accumulator X instruction. That way, every instruction one after the other has been loaded into this memory. Let me repeat once more that I have assumed that this is a byte oriented memory. That means every byte has an address and every byte is addressable. Of course, if we want that, we can fetch one word also. That means instead of a byte, if we want, by one word I mean 2 bytes taken together, that means 16 bits, okay, or 2 bytes. For example, if you want, then this 0F00, that is in the location 0303 and 0302, these two taken together, this one word can also be taken out of the memory. Therefore, let me repeat that I am talking in terms of a memory which is byte oriented, in the sense every byte is addressable, but if we want that, we can take out or push in either 1 byte or 1 word consisting of 2 consecutive bytes. Okay, that is the assumption that I'm meaning whenever I'm talking about the memory and say accessing the memory to take something out of it and to write something into it. Now, once these instructions has been loaded, which will be loaded by means of a loader, okay, from possibly that secondary storage, floppy disk or hard disk, as you know. Once it is in that memory, the computer will start executing this program. Okay, let us see how these computers start executing this program. Now, let me import what we call a central processing unit. Okay, few of the components of the central processing unit I have shown here. One is that arithmetic and logic unit. The accumulator that I'm talking of, I'm assuming that accumulator is of 16-bit long, that means 2 bytes wide. This is what a 1 byte wide register. Okay, we call it instruction register. Let us see what is the purpose of this instruction register. Here is a 16-bit or 2 byte wide another register, we call it program counter. Okay, all these registers, that accumulator, instruction register, program counter, has special significances, as we will see. There is one address buffer that we have kept, and there is one data buffer we have kept. Now, whatever I have introduced till now, you can see that it's a little bit simplified picture of a computer. I am gradually trying to bring in components, systems and subsystems which ultimately make the computer. Naturally, to start with, some simplifying assumptions have been made, as I am telling, okay, and you will see later on that how actually gradually these simplifying assumptions we can remove to come to more or less the actual picture. Okay. Now, between the CPU and the memory, naturally there has to be some kind of interconnection, and let me assume that what we call a bus, okay, as a bus exists between a central processing unit and the memory, so that informations, I mean that by that I mean the data as well as the instruction can be transferred between the central processing unit and the memory. Now let's see how these programs will be executed. Okay, to start with, somehow the program counter, which is a special register, okay, and special counter which keeps track of which particular instructions is going to be executed next. Okay, to repeat once more, the program counter is a register which keeps which contains which instruction, the address of the instruction that is going to be executed next. This program counter is loaded with the first instruction that is to be executed. That means the program counter is now containing 0300. Okay, the program counter now contains 0300, which means this is instruction, that instruction is going to be executed next. Okay, right. Now what happens is that whatever is the content of the location pointed to by the program counter, that means 0300, its content is taken out, we call it fetched from that memory, okay, and is brought into the instruction register, from which address that memory locations is being accessed. Okay, and that means from which address the content of a memory locations will be taken in is kept in that address buffer, and the data buffer's responsibility, okay, is that all information, that means any data or instruction that is passed from the memory, or any data that goes out of the memory, okay, will go through the data register, and these two are connected by means of this bus. Okay, we call this bus, right, to the memory. Okay, therefore whenever I say that the content of a memory location is being fetched, okay, or is written into, we always will mean that the address of that memory locations will be in that address buffer, and whatever data is passing between the central processing unit and memory will go to the data buffer, right. Now therefore the content of 0300, which is the content of the program counter, now will be fetched. Okay, the 01 will come and will be loaded into what we call that instruction register. That instruction register therefore contains the instruction that is being executed currently. Okay, therefore 01 is here. Content of this instruction register is now decoded to C. Okay, therefore there will be another unit which is a decoder, okay, which will decode the content of the instruction register to know what is that instruction that is being executed, and seeing that it is an in instruction, right, seeing that it's an in instruction, it will input from some external device through the data register a value into the accumulator. Okay, and the execution of this instruction is over. Therefore, the execution of this instruction, right, that means this in instruction which I am executing now, say this in instruction which I am executing now, will be consisting of two parts. Okay, one is that first the instruction is fetched, okay, into that instruction register. On knowing that what is this instruction is, that instruction is executed. Therefore, the instruction cycle, so to say, consists of two parts. One we call that instruction fetch, another we call that instruction execution. Okay, Now we'll see that this instruction execution itself will take several sub-steps, okay, before that instruction can be executed. Here we have, now I'm saying that as if that instruction being executed, okay, it's one simple process, okay, single process. Now after, say, this in has been taken in and executed, by the time that content of memory location 0300, that means that instruction is fetched into that instruction register, the content of the program counter is automatically incremented to the next memory location. Therefore, this is important that whenever an instruction is fetched, the program counter is automatically incremented to the next location. Therefore, by the time this instruction in has been executed, the program counter is now pointing to the next location 0301, which is the address of the next instruction, the store accumulator, the 04. Therefore, in the next instruction cycle, the content of the program counter is once more taken, that means fetched. That means 04 now is coming into the instruction register. By the time that 04 that has come, so for example, now 04 has come here into this instruction register. By the time this 04 is, this instruction register is decoded, the program counter is automatically incremented to point to the next location, right? Now, 04 has come here. The instructions is being decoded, and on decoding it knows that it is a store accumulator instruction, okay, and therefore it needs the address of the memory location where the content of that accumulator has to be stored now. The address is obtained from the memory location pointed to now by the program counter, which is now say 0302 and 0303. The content of these two memory locations will be taken together. 0F00 will be the address, and in this address whatever was inputted into that accumulator will be stored. If I assume that input was 0500, then the content of this memory locations will be 0500. That means that X data, okay, will consist of 2 bytes. The higher byte is 05 and the lower byte is 00. That means the data is 0500. This is the way this program will be executed step by step. After that, this instruction execution is over. That means the program counter was here, it was fetched, then the program counter was pointing to this location, then this location and this location content will be read, okay, into that address register, and its content now will be put to the, its content will be now used as an address of the memory location where the content of that accumulator will be pushed in, right? And by the time this is done, the program counter will be automatically incremented to the next memory location, which is now pointing to in. Let me just clarify once more here that as an instruction is executed, the program counter is automatically incremented 1 byte at a time, so that at the end of execution of an instruction, the program counter now points to the next instruction that will be executed, okay, which means that after the store accumulator X instruction is executed, okay, the program counter will automatically be pointing to in. Now this in will be executed once more, which means the content of, the input will be done from some input device into that accumulator here, right? As a 2 byte has been read, then program counter as it is done will be incremented to the next memory location. Then this content of this program counter 04 will be inputted, fetched into the instruction register, which will be now decoded, and which means that it's a store accumulator instructions once more. The address will be obtained from the next two memory location, which will be pointed to by the program counter one after the other, right? And at the end of this instruction, the program counter will automatically be pointing to the next instruction, which is load accumulator X instruction. Okay, this way that instruction will be executed one after the other. Okay, content of the program counter will be sent to the address buffer. That address buffer will point to the memory location. The content of that memory location will come into the data register, and from the data register it will come into either an instruction register, as I have said in the case of a instruction fetch instruction, or into that accumulator if I am executing, say, in instruction, or the content of accumulator will be go into the proper memory location as the instruction dictates. Okay, here we have taken that way, one after the other all these instructions will be executed. Here the store accumulator will store something into that Y. Add memory will take the content of X and the content of Y and will be loaded into the memory location 0 of F02, 0 F, sorry, it will be stored in that memory location by store accumulator Z 0F04. That means this is the memory location 2 bytes designated as Z, and that way this entire instructions will be sequence of instructions will be executed sequentially, and program counter will always keep track of which instructions are being executed next. Now from this we can see that the execution of any instruction essentially therefore consists of two steps. One is that instruction fetch and decode, and the other is that instruction execute, and we call this a basic instruction cycle. And this concept, that means keep the program and the data in the computer memory, and then the central processing unit executes it, okay, is in essence is a stored program concept introduced by John von Neumann in 1945, and it's called the von Neumann machine. Okay, this is the concept of a stored computer program, okay, stored program computer, and it still is in vogue. Okay, mainly what we do is stored program concept that we employ to design a computer. Now let's see, we are talking about that instruction cycle. Okay, basically we say that as if that instruction cycle consists of two steps. One is that instruction fetch and decode, another is that instruction execute. Okay, but naturally that these two steps are divided into some more sub steps, and I have seen a bit more detailed diagram of an instruction cycle. Here you see that it's an instruction fetch, okay, where the instruction has been fetched, right? After that instruction has been fetched, the opcode is decoded, that means the decode operation is done, and by the time you see the decode operation is done, the program counter is incremented here. Okay. Now then is a get operand address. When you get that operand address, the operand address mainly will be, in this case, as you're saying, that was pointed to by program counter. Therefore, as I'm getting that operand address, the program counter in this case was incremented twice. You see that as I get the operand address for store accumulator X, the operand address in fact was pointed to by the program counter itself. It will be incremented twice, first to this location and to this location, so that by the time that the store accumulator X instructions is executed, the program counter is pointing to the next instruction, right? Therefore, we get that operand address. Now fetch the operand. I mean, not that all these steps, for example, this is a situation in the case of an add memory Y, right? Here the operand has been fetched, that Y has been fetched, right? Then the operation is done. That means the add memory operation is executed here, and then store operand. Now, since it's an accumulator based machine, okay, the operand is automatically stored in that accumulator, and then we get the next instruction address from the program counter, and that instruction fetch starts once more, right? And therefore, you see that this instruction cycle, typically for say that add memory Y that we have shown, this is a typical instruction cycle that computer goes on executing one after the other, right? That is, takes an instruction, decodes it, gets the operand address, fetch the operand, do the operation, store the operand, and then get the next machine instruction. Okay, it goes on the instruction cycle one after the other till the instruction to the total program is executed out. Okay. Naturally, many of these steps may have to be broken down into sub steps, as we will see. Okay, as the necessity arises, we will discuss them one after the other. Now, as I was telling here, this is a program that was more or less, why more or less, that is a sequential flow of control. That means one instruction after the other, as has been sequentially put into that memory, starting from the memory location 0300, is being executed out. But what happens if there is a branch kind of instructions? For example, if there's an if instruction, if there's a go to instruction, let us see what happens then. Okay. Here I have taken a program which consists of an if instruction. It's a high level language program. More or less it's in the form of, say, that C language program. That if I say that if A greater than equal to B, then I execute X equal to X minus Y, else I execute Y equal to Y minus X, right? And then I execute P equal to P into Q. Okay. Therefore, this is a high level language program which consists of what we call that alternate statements, which have to branch out as is necessary. Okay. Now, the corresponding assembly language code will be like this here. Let's say load accumulator A by the content of a memory location, just to get the value of A, then subtract memory B to see that whether A is greater than B or not. Okay, here we have subtracted the content of memory location B from A. Now, this operation is not stored anywhere. Okay, even if it's stored, what important thing is done here is this: as the subtraction takes place, a flag is set. Okay, a sign flag say is set. Okay, the sign flag setting to 1 means that the result is negative, and the sign flag 0 means the result is positive. Right. Now, naturally, you will have to take a jump. If the result is negative, okay, then we should come here. But if the result is 0 or positive, then this instruction should be executed. Okay. Therefore, you can think of that as if there are two flags. One is a 0 flag, and there is a sign flag. Depending upon that whether the 0 flag is set, that means if 0 flag is 1, that means the result is 0. If the 0 flag is 0, then the result is non-zero. and if it is non-zero, the sign flag will determine that whether the result is negative or whether the result is non-negative, right? Therefore, as the subtraction instructions is executed, right, these two flags will be set. There may be some other flags which we will know later on, but we will need these two flags only now. Now, this says that jump on negative, right? That means if the result is negative, then jump to label 1, that it jumps from here to here, okay? But if the result is non-negative, then this is executed. Therefore, this constitutes a two-way jump. Jump negative, it comes over to here. By negative, you mean that if the sign flag is set to 1, okay? If its result is greater than or equal to 0, right, then what is done is that this instruction is executed. Then load accumulator X, subtract memory Y, okay, oh, sorry, not this one, this instruction is executed. If A greater than or equal to B, this instruction is executed. Therefore, load accumulator X, subtract memory Y, and the result is stored into result of the accumulator, which is in the accumulator, is stored into X, right? Else, that means jump on negative. If this is result is negative, it comes over to here. It executes this instruction. That means load accumulator Y, subtract memory X, and store accumulator Y. That means this result is stored into the accumulator Y. Now, one thing you see that if this is executed, then this will not be executed. From here, the control should jump from this point after execution of this instruction to P into P equal to P into Q. Therefore, a unconditional jump, that means jump to label 2 is executed. That means after executing this portion, automatically it will jump over to execute P equal to P into Q. But if there is a jump conditional, that means jump negative, then it will automatically, on taking sign bit to be 1, will come to this particular instruction. This will be executed sequentially, and then automatically the next instruction that will be executed is this one, right? Therefore, you see that a control construct like if, else can be translated into assembly language code like this by means of jump conditional or jump unconditional instruction into this form. Okay, this is once more a typical example, right? Not pertaining to any particular machine. An example that, so to say, that I have created to show you that how in such cases that a translator, high-level language translator, translates the high-level code into machine language code of our machine. That means an accumulator-based machine, okay, and which is a single address machine. By means of a single address machine, as I say, that at most one address you can specify. Now, we'll elaborate on this particular example in our next lecture.